Joining us, start the recording here. If Zoom kicks me out unexpectedly, then that will be the 5th time that's happened today. So I apologize in advance. If I get frozen, please, if you can, tell me. I may not get the message, but we'll try. I can normally tell if I'm frozen because I see 25 faces all do this at the same time. So that's my cue that like something has gone awry. But in case I missed said cue. So homework. I wanted to start with that because continuing questions on homework. So I sent out a note yesterday about the checking against the saturated means thing. So here's the longer version of the story. In this homework, I used to have a second model in section 1 in which I asked you to do saturated means and get the F-test and the usual things we did in the other homeworks. And I had previously had this assignment use ML instead of REML so that you could do a likelihood ratio test of how your fixed piecewise slopes fit not worse than the saturated means model. And that was because I knew that that would work. Like that would be easy, like relatively easy, and likelihood ratio tests were a thing that would have been, good solid territory by this point in the class. But then earlier in the semester, I discovered that in Stata, you cannot use maximum likelihood with Saturn with degrees of freedom. It just flat out won't let you. So then I had to decide, all right, how am I going to make this comparable across the 3 programs? I decided, okay, we'll just use REML and we'll do this kludgy put the dummy codes in thing. Well, it works from the perspective of the F-test. So the whole point of putting in dummy codes for individual occasions is to saturate out the remaining degrees of freedom with respect to what the possible means could be, and then do a joint test of whether those dummy codes add to the model. And if they add to the model, that is bad, because it means your model wasn't good enough to recreate the means in the first place. Cough, cough, homework question. But it turns out that for the perspective of just checking the -2 log likelihood as to whether your model is correct, you do get slightly different values if you use different occasions. So I'll just tell you the answer. Just use occasions 1 through 4 and 11 through 13 because those are the ones that I arbitrarily picked when I built the answer key, and those ones will give you the right -2 log likelihood. Now I know at least one of you emailed me about the F-test thing. Would that be helpful to talk about how to get that F-test? Yes? All right, then I will remind you where you can look to get an example of where that was done. It was in, am I sharing the screen yet? Of course not. I turned on the talking thing, but I forgot the screen share thing. Please?
You're frozen.
Yep.
So who's taking over?
Katie.
I
But
pass.
she does
I
not
pass
want
hard.
to. Yeah.
Did anyone get the right p-value but not the right?
Okay, there, the recording's back on. The F-test for the joint contribution of the new dummy codes is in contrast in SAS. So SAS folks, wait, am I back? No.
Yeah. We can hear you.
You can hear me, okay.
Yeah.
I'm getting the angry hourglass again. The F-test is in contrast, where each slope is listed with a 1 after it. And there are commas that delineate the numerator degrees of freedom, the number of slopes to be combined. So it's like S41, comma S51, comma S61. That's how you lump those three slopes together. So if you're using, wait, the hourglass stopped. Are we here? Are we really here? It's like, all I want to do is teach statistics, damn it. I don't want much in life. I just want to be able to see you and talk to you like normal people. Oh, goodness. Lord Almighty. All right. So those of you who are using SAS, this is super easy. You just write your 7 things with a 1 in there, right? And it's fine. Those of you who are using Stata, also super easy. It's the test statement. So the line that says test, S4 equals 0 in parens, S5 equals 0 in parens, S6 equals 0 in parens, comma small, because that gets you the right degrees of freedom, which means you get the right p-value. Okay, so SAS and Stata people, any questions on those 2 snippets of code on page 15? Okay, people using R, you are going to hate this. But I am just the messenger. So contest MD. MD stands for multidimensional. So when you're asking for a linear combination of fixed effects or multiple fixed effects at the same time, it's 1D for one thing and MD for multiple things. You have to do this R bind of things, row bind of column vectors. I think that's it. I can picture the table that it ends up being, but you have R bind, which means stick all this stuff together, and then the individual things have zeros and ones where you need as many numbers as you have fixed effects in your model. So at this point in the homework 4, you need like 13 zeros in each of these to start with because there's 13 fixed effects. Yeah, I know. I told you were going to hate this. And you would selectively change one of the 0 values to 1 for each of the dummy codes that you added. And double check your output as to the order of these things. Because I also found out that R reorders them relative to how you write them. I found that out in our next example. Yes. Because I write them in a certain order that corresponds to like conceptually what they represent, and R reordered mine. So check your output to make sure that they're in the right order, and that's how you know where the zeros and ones should go. And so you'll have to write like 6, 7, however many it is, sets of these 13 zero thingies. Fun. Okay. Questions on homework? Otherwise. Not right now? Okay.
I actually do.
Hit me.
So the section, let's see, 4 has I know you talked about the instantaneous linear rates last time, and I even went back and listened to that again. But I'm still not doing something right to get just the instantaneous fixed linear rates correct.
Okay. We'll go back over. Let's see. I'll open up the spreadsheet.
And I even compared it to like the quiz on Icon, what you had us do for that. That was helpful to remember.
They are very much the same. It's just that there are extra terms in this model that have to be disregarded if they're not active for the occasion that you want the slope for.
Okay.
So I'm not sharing yet because I don't want to jinx anything, but this is the spreadsheet I sent out yesterday that we've been looking at. The recording for the class, by the way, is going to capture what I'm looking at. So if you want to see this again, or for those of you who are not able to attend. But so like if you want the instantaneous linear slope, say at the first occasion, then of the slopes that are currently in the model, only the linear and quadratic fixed slopes for the before phase 1 to 7 are relevant at occasion 1. The others are irrelevant. They're not part of your estimate statement. And so then the slope that you're trying to ask for always gets a 1. So you might have been accidentally filling in the value of time for that instead. That's a common mistake.
Yep, that's it.
And so then the quadratic slope gets multiplied by, everybody say it with me, fingers or audio. The quadratic slope is multiplied by 2. Yes, it is for the value of time that you want it for. Yep. And so it's the exact same structure as in the prior formative assessment where we did this in the context of just a quadratic model. The same is true for this because the other slopes are irrelevant for occasion 1. They're not active yet. So any of the terms related to them would be 0 because in your data, those predictors are coded 0 at occasion 1. And I'm frozen. Of course I am. Okay, this thing needs to get out of the way. There we go. I'm on slide 21. So in this model, this is an example of what it would look like to add 2 predictors that are time invariant to a model. So I have years of education as an example of a quantitative predictor and group, which in this case would have to be a binary group so that there's only one slope that's relevant to distinguish 2 groups. You'd need more than one slope if there were more than 2 groups. And I have those 2 terms entered in each of the level 2 equations. So which gammas, here's a quiz for you, reflect the main effects of education and group? Like if you wrote the model in R or SAS, if you wrote education by itself and you wrote group by itself, where are those in here? Can I repeat that? Yes. So we're trying to get acquainted with the equations. And there are 3 different effects of education in here, and there are 3 different effects of group. So which of these sets of effects here refer to the main effects of these variables? Like if I wrote out a linear model, like the model statement in SAS or in Stata, if I just had education by itself and I had group by itself, which fixed effects correspond to those ideas? And we have a guess, 00, 01, and 02. Yeah, so the fixed intercept is 00, and then 01 is the slope of education as a main effect on the intercept, and 02 is the slope of group as a main effect on the intercept as well. So then if I typed out education by time and group by time, where are those? We have one guess, 1, 1, and 1, 2. Ding, ding. Then that leaves these things. What are they? What's 2, 1, and 2, 2? Quadratic time. Yep, these are 3-way interactions. Education by time, and group by time. Yes, indeed. If I wanted to add something like education by group, what if I felt like group differences were different based on your education level? Where does that go? Education by group is a purely level 2 interaction because both of those variables are level 2. Where does it go? We got 1 vote for the second line, education by group. What does the second line predict? The Second line is predicting beta 1, which refers to what? Beta 1 is the linear time slope. So, but if I just want education by group, and time's not in there, then it can't be the second line. Has to be the first, yeah. So education by group would go into the first line. The second line would be education by group by time. And the third line would be education by group by time, which would be a four-way interaction. Yeah. So do you remember at the very beginning of the semester when we spent a few minutes reviewing interaction terms and how you figure out what main effects are and what they mean? This is why. I knew this was coming. And yes, it's not at all uncommon to get up to a third or fourth way interaction because of time and the role of time in these models. So yeah, it gets complicated very quickly. In terms of the role of these things here, one way to think about what their job is to think about which source of variance any one fixed effect in your model is supposed to explain. So how many piles of variance are in my model here as it's written? How many variance components? Piles of variance? 4, yeah. In other words, how many blue things? I've got an E at level 1. I've got 3 different U's at level 2. That also means I have their covariances as well. But that means there's 4 kinds of variability. So how do I know then, for any given fixed effect, which one is supposed to be reduced by that fixed effect? Do you remember the answer I told you last time? The one in its line. So I wanted to do a little bit of a review / visual of that. For those of you who may not think in equations, if you're more of a visual person, this one's for you. So once upon a time, at the beginning of the semester, we started with an empty model. And the whole point of an empty model is to talk about how much of the variation is level 2 between persons and how much of the variation is level 1 within persons. So I have these 2 circles here on slide 22 are meant to represent that idea that we begin by taking the overall outcome variance and partitioning it into 2 sources, 2 orthogonal sources, meaning uncorrelated. Level 2, random intercept, and level 1, residual. Okay, with me so far? Okay, then what did we do next? Wait for the animation. Oh, it worked! We added a box. So for those of you who've had SEM, it's not a coincidence that I'm using boxes and circles. Boxes are observed variables and circles are pretend variables, of which these things are variance components are. So we added level 1 time. And level 1 time is supposed to reduce the variable, the variance in its line, right? E variance. So part of the reason why people may show within person fluctuation is because there's change on average. And so rather than having the same flat line across time for everybody, we make it a straight line, whatever direction here, and that hopefully should reduce some of the E variance. It's evidence that we had change on average. So then what I would call this is a fixed linear time random intercept model at this point. So anytime that you add a fixed effect, the goal of the fixed effect is to explain variance at its level. In this case, time is a purely level 1 variable because it's balanced across persons in this example. Therefore, it only can explain level 1 within person residual variance. Okay. Remember what comes next? Random. Am I frozen? No? I'm just that boring. I was expecting some kind of a reaction for random. Thank you. Yeah, it can be fake. At this point, I will take a fake reaction. It's fine. Because yeah, now we've added something to the model. If we add a random time slope, we are not explaining variance. We're making a new pile. And where that pile comes from is the residual. Part of the reason why people were deviating from the trajectory that was predicted for them is maybe they need their own trajectory. So giving people a different slope explains, and I'm putting that in air quotes, level 1 variance. But it doesn't really explain it from a mechanistic point of view, because you still don't know why people need their own time slope variance. It's just another kind of error. So what we used to have in terms of, let me go back. See, I had a big level 1 residual, and now it's smaller because part of it's over here. Come on, I get credit for cleverness. I can't draw for shit, but I can do PowerPoint thingies here. So now at this point I've got 3 different kinds of variance. So in, say, homework 3, the next thing that we did here, adding on to our random linear time model, is add in time squared. Time squared is a purely level 1 variable. It should explain some of the E variance left over. Why are you off your line? Well, maybe you need a bendy line. If we make the line bendy, then the E's should work out better around it. So quadratic time explains level 1 variance. And then, if we have fixed quadratic time, we can have random quadratic time. And E gets even smaller because part of it has again been allocated to level 2. So why are you off your line? Even though I made a bendy line? Oh, because I need my own bendy line. And that's going to reduce my error variance and move it over here. So this is where we get to the original 4 piles of variance to be explained by the level 2 predictors. So starting with a random quadratic unconditional model of time, at this point, these random effect variances, U0 for the intercept, U1 for the linear slope, and U2 for the quadratic slope, they represent a new baseline. They are all the reasons why people differ from each other. It's as much variance as there's going to be. So it's analogous to what I would say in an empty model in a regression context, where the residual variance in an empty model is all of the variance in the original variable. Analogously, each of these is all the individual variance in these particular growth terms. So then we add predictors. So here's my pile of predictors. I'm going to move them around and put them where you tell me to. Okay, ready to play? Okay, here's my first one. The main effect of education, and I have in parentheses here, education by intercept, is because that's how I think of it. The role of the main effect of education is to moderate the intercept, to make it go up or down. Which of my little, my circles here should I put this one on? Which source of variance is the main effect of education going to explain? Should I put it down here on the level 1 residual? No. Should I put it here on the level 2 intercept? Yes, I should, because that's what's in its row. Why do some people need different intercepts? Well, because of their education. Likewise, group by intercept. Does it go down here? No. Does it go over here too? Sure it does. Group by intercept. Why do people still need their own intercepts after controlling for education? Oh, because of which group they're in. And so at this point, I can calculate a pseudo R-square for, relative to the original circle all by itself, how much of it has been explained by these 2 new predictors, and how much of it is left. So the idea of pseudo R-square means per pile, how good did your model do? So that's why it's useful to know how much intercept variance was there in the first place to be explained. How about this guy right here? Level 2 education by level 1 time. This is known as a cross-level interaction because it occurs between predictors measured at 2 different levels. Does it go over here? On my quadratic time slope, does it go over here? Oh, we got some ambivalence here. We got some no's and some yeses. So I'm guessing you think it could either go here or it could go here. The answer is that it does go right here. Now, why is that? Conceptually, this circle right here, U1 as a random variable, the variance across people being the random linear time slope variance, that is, why do people change differently to begin with? Maybe some people change differently because they have more education or they have less education. So education by time, the job of it is to explain the time random variance. They match. Likewise, group by time, its job is to explain the time random variance. And now I have another pseudo R-square that's possible. Of all of the reasons why some people changed faster initially at time 0, how much of it was because of education and how much of it was because of group? And how much is left? Okay. Last but not least, education by time squared. Up here. Yep, far right. Far out, far right. Far gone. Far go? No, just checking to see if we're frozen. Okay. Yeah. Time squared by group. Question, if I add level 1 times squared, does it alter level 2 variance? Level 1 times squared was already put in the model as a fixed effect, and then it was given a random effect, which is what formed this variance component. So that would have already explained residual variance, and I see a typo in this. I'm going to fix that. Is that what you meant by the question?
It might be easier to just talk.
Yes.
So I guess my question is more so like if you add a random like linear or whatever, it reduces the variance at level 1 because it gets partitioned out.
Yes.
So is it only when you add to the higher, like level 2, or like whenever you add something? Oh wait, never mind. Nope, never mind. Get it. I got it.
Okay. Glad you could talk yourself through that one while I smile at you. You know, that's
Okay.
a good outcome.
Yeah.
I think what you might be asking is like, would the residual variance at level 1 be explained anymore?
Yeah.
Is that where you were going?
Yeah.
And what kind of predictor would that have to be to explain level 1
Within
residual?
person.
Within person.
Within person.
Remember the E is why are you off your line today? Today. Like, why is Zoom not working today? It can't be anything that's like common to me because it worked Tuesday. Like, what is going on today? A time varying level 1 predictor would have to explain this level 1 residual variance. Yep. So level 2 predictors explain level 2 variance related to what they are moderating. So if we have education as a main effect, that's the same thing as saying education is moderating the intercept. It explains intercept variance. If I have education by time and I have a random time slope in the model, then that is what it's moderating and predicting. And the same thing with time squared. So they match. Now what about this one? The terms that I added hypothetically to the previous model. What if I had group by education as a two-way level 2 interaction term? Where do I put it? Group by education as a new term in the model. So you got one vote for the first bubble. Ask yourself this, is the word time in there anywhere? If not, has to be the first bubble, has to be intercept. Second one, is the word time in here anywhere? Education by group by time goes here. And because time squared is in here, it goes here. So cross-level interactions are designed to explain the random slope variance of the level 1 predictor in the interaction. Because time has a random slope variance, interactions with time explain that variance. Because time squared has its own random slope variance, interactions with time squared explain that variance. Okay, with me? Baby? Is moving around boxes helpful at all? Yeah, sometimes it's nice to get a break from the equations, right? So now what would happen though? Okay, so going back to the model, this is the type of model we were talking about here for a second, where the rule is any fixed effect explains the variance that's in its line, right? That's the rule. And so then in the last class, someone asked, well, what if there's no u here? Then where does it go? So let's tackle that situation. What if my model looked like this? What if I have a fixed quadratic random linear model instead on slide 28? Education as a main effect? No, don't, no. No! Come on, come back. Okay, there, I'm back, right? We're here? We're here, we're gonna do this. That kills me. Okay, so fixed quadratic random linear. So I don't have a quadratic variance pile to be explained. So level 2 education and group as main effects. Anything different there? Nope, they go over here still. Level 2 group by level 1 time and level 2 education by level 1 time. Anything different there? Nope, they got the word time in them. Time is random, so we'll put them down here. Make it look like the other picture for a moment. There we go. Now these guys. Stop it. Hello? I don't have anything to do. What am I gonna do? Where do I go? Yeah. Residual. People don't have their own quadratic. It has to be residual. They get thrown away. Nah, they get reviewer 3 wondering why you're putting them in the model. So this is a source of controversy because exactly this. Why are you trying to explain individual differences that don't exist? If people don't need their own quadratic time slopes, what are you doing? That's my impression of reviewer 3. And they have a point. But the response is, but I had a hypothesis about this and it's not my fault that it wasn't significantly random and I have low power and please? But yeah, in terms of coming up with an effect size, it's out of E. And then that might seem crazy that a level 2 predictor could explain level 1 variance, but that only happens when it's part of a cross-level interaction that doesn't have a random slope. And it does make sense if you go back to this slide right here. In the unconditional model, when we added time squared, and if we added a random quadratic effect, this bubble came out of residual. That is where it came from initially. So if you don't have that bubble in your model, then you're going to explain the variance it would have come from. So when that might happen is like if you test this bubble and it's not significant, meaning it looks like that. Nope, not the bubble. I want to take the words out. That's not going to work. If it looks like this, right? There's not very much random quadratic variance. It's not significant, doesn't do anything. So it's like it would just be, hiding in there still. But what that does mean is that any cross-level interactions could potentially have incorrect standard errors to the extent that this really is a sizable variance component, but you don't have enough power to detect it. So there is a bit of controversy on what to do here. But I think you can make a reasonable argument for either size in terms of whether or not it makes sense to put those boxes in the model. Is that the case for any type of predictor that does not have a random slope? Yes. So in terms of procedure, anytime that you are interested in testing a cross-level interaction of a level 2 predictor with a level 1 predictor, like education by time or education by time squared here, always, always, always you want to test the random slope of the level 1 predictor first and keep it in the model either if it's significant or sizable enough if you have a small sample. Then you will have a better chance at having correct standard errors for that cross-level interaction. If you test a cross-level interaction with a predictor that does not have a random slope, but it should have, way too high type 1 error rates for that. Way too high. Okay. Questions? So we have equations, we have pictures, and then words. Words, words, words. So this is me trying to boil down the demonstration that I just gave you. So rules for a pseudo R-square. Which variance component should be targeted by a given new fixed effect? If it is a purely level 1 fixed effect like time, it explains residual variance at level 1. If it is a purely level 2 effect, like a time invariant predictor in this case, its main effects and interactions amongst level 2 predictors reduced intercept variance at level 2. And like education by group as a level 2 interaction also reduces intercept variance. What happens to cross-level interactions depends on what is in the model with respect to the level 1 predictor within the cross-level interaction. So if that level 1 predictor is random, then that cross-level interaction explains that corresponding random slope variance. So like if we had linear time as being random, then group by time, education by time, group by ed by time, all of those things predict the random time slope variance at level 2. So random trumps fixed. Yes, it does. I believe I said that at one point in the semester. But yeah, it does. Random trumps fixed. If the level 1 predictor is not random, if it does not have a random slope, then any cross-level interaction with it predicts residual instead, because that is where that random slope would have come from in the first place. It's still buried in the level 1 residual. So in this case, if I had time squared that does not have a random slope, then group by time squared, ed by time squared, group by ed by time squared, any of those things reduce E variance at level 1 instead. So this is a lot, am I right? And when you are in a model that has lots of variance components, it can be very challenging to convey this in a way that is understandable and succinct. I have a paper in which I believe there were 8 variance components because it was a 3-level model, and I did not want to have the conversation as to which of the 8 a given term explained and why with the reviewers. So I did something more straightforward instead. Let me introduce you to total R-square. Do you remember the original definition of R-square in regression models? Proportion explained variance is one of them. But do you remember the other? If I wanted to talk about R-square as a correlation, I know at least half of you have talked about this with me. R-square is the squared correlation between what and what in a regression model. No? Yeah, predicted outcome and actual outcome. Ding, ding, ding. So y hat as the predicted outcome and the y. If you were to ask your software, every software package can do this, even SPSS. Oh, SPSS slam, she went there. Ask your software package to build you a column in your dataset of model predicted outcomes. You can take that column of your dataset and ask for a correlation with the real outcome. That's R. And if you square it, that's model R square. So let's just do that. Can we do that? Yes, we can. So as a simpler way of describing effect size, you can do total R square, which is exactly what I just said. You ask for a saved column of model predicted outcomes from the fixed effects only. This is critical. Not with the random effects. So in each of these software packages, you have to make a distinction as to whether the random effects get included. Only fixed effects. And then we take that column of predicted outcomes, we take the real column, and we correlate them, square that correlation, and that's R square. On the plus side, people know what the hell that is, right? People know what R square is. You can talk about, of all of the variation in response time, or well-being, or stress scores, X% of it was explained by my model predictors, right? People know what to do with that information. On the minus side, you lose the nuance of how well your model is working at each level and for each source of individual differences. So if you found out that some people change differently than others, how good did your model do in capturing that specifically? Total R squared doesn't tell you that. So in practice, I think it's helpful to report a combination, to report the explained variance in each of the sources of variance, and then maybe a total R square for a marginal, sort of overall, how well did the model do? Can you guess why I say no random effects in the prediction? Any guesses? What would it mean if I calculated a total R square from a predicted outcome created from fixed and random effects? Does that make sense or no? Because there are some people who will do this. I've actually fought with Jonathan about this before. And I will die on this hill that random effects do not make any sense. Wouldn't that give you the actual outcome? It would give you something much closer to the actual outcome, but not the actual outcome because E would not be included. But that actually makes part of my point. If you're going to include all the random effects, why not include E too, right? Why leave that guy out? It's like, well, let me get this straight. You want to include some of the error terms in your explained variance, but not all of them? Yeah, no, that's not what explained means, right? The fact that we know that people change differently, we don't know why they change differently. It's still error conceptually. So I will die on this hill that an R square that includes random effect variance makes no sense. Now, that being said, there are people who will fight with me about this. So I have given you a set of readings for a newly published suite of R-square measures. That includes slope variance as explained variance in some of them. And they also, in this set of measures, it's Jason Reitz and Sonia Sturber are the ones who came up with this. They have a way of calculating pseudo R-square that makes it not go negative. Because rather than dealing with the original amount of variance in a random effect and then seeing how much is left, the total is based on the marginal variance that includes the fixed effect. So it's a different way of calculating it that solves the negative R-square problem, and they include variants of this that have slope variance as well as variants that don't. So I'm just giving this to you as another set of ways that people talk about R-square. And in the original paper, they have a lit review that has like 27 other versions that people have put out there in the multi-level modeling literature. So the take-home message for all of this, by the way, the moral of the story, if you are going to give any kind of R-square from a multi-level model, be very, very clear about which one it is. I would literally give them the formula for how you found it and give a reference so that people know exactly what you mean. So it gets very complicated. So I'm going to give you total R-square. I'm going to give you pseudo R-square. The nice thing about this approach that they have here, there's an R package that they made that spits this stuff out for you. So that makes it a lot easier to get these different types of R-square measures than what it would otherwise be. So fun with effect size. Otherwise, effect sizes can always be obtained by taking the t-test for a given fixed effect and converting it into a D or an R. So you can always do that too. All right. Yeah. Nah. I don't have the strength for this today. Questions? Wait, what is a D? Cohen's D, standardized mean difference. There are formulas by which you can take any t-test and using the degrees of freedom for the denominator to back translate it into an R correlation type effect size or a D standardized mean difference effect size. So you can always do that for any set of fixed effects in a model as well. All right. Questions, comments? One last question for you then. Do I have to test whether or not the slopes of my level 2 predictors are random? Let me go back. Like the slope of education or the slope of group, could they have a random slope associated with them? Level 2 education and level 2 group in a 2-level model. Can those effects also have random slopes associated with them? Thumbs up for yes, thumbs down for no. We have some hesitancy. I'm seeing, yeah. So in a 2-level model, can level 2 slopes be random? No, they can't. So think of it this way. Each person can have their own time slope because each person has multiple observed values of time to make an x-axis out of to get a slope out of. But the definition of a time invariant predictor is that each person has one value. They've got a dot, not a line. So there's no way that each person can have their own effective education because education is a constant for each person. So level 2 predictors cannot have random slopes in the traditional sense. They can be used to predict heterogeneity of variance, and the way to do that looks a lot like a random slope, but that is a different concept done for a different reason. So 99% of the time, you will not ever see level 2 predictors in a 2-level model have random slopes. In a 3-level model, though, they can. All right. Anything else before we call it a day, before Zoom cuts me off again? Because I know it's going to happen. It's just a matter of time. But there can't be a 3rd level random slope in a 3-level model, right? Correct. So if I have a 3-level model, then level 3 predictors cannot be random. If I have a 4-level model, level 4 predictors cannot be random. But if I had a 3-level model, level 1 predictors can be random over 2. They can be random over 3. They can be random over both 2 and 3. And level 2 predictors can be random over 3. So lower level things can be random over upper level units only. Vomit. Yeah, I know, Kelly. I didn't make the rules. It's not my fault you have a 4-level model that you're trying to work on. True story. But that's good news for like the rest of this class, because we're not going to have to add any random slopes for our level 2 predictors. So, you know, that does simplify things like this much. As much as you could call this simple. How many different predictors are in this model, by the way? Like concepts of predictors. How many predictors are on this slide 21 here? One vote for 2. There's 2 level 2 predictors. There's 3, because time counts. How many parameters are in this model? A lot. And there's only 3 predictors. So, yeah, it gets complex quickly. All right, then office hours start now. Let me know if you need anything. Have a good weekend, and I hope to see you next Tuesday. Homework is due on Monday. Let me know if you need anything. Thanks, everybody.